Assalamualaikum and a very good day. Today we will have another lecture for the MME6174 Design for Manufacturing and Assembly course. So today we will talk and discuss about the product design for robot assembly. So as with the product design for high-speed automatic assembly, one of the objectives with the robot assembly is to provide the designer with the means of estimating the cost of assembling the product. But in this case, we are using the robots. Yeah. However, several important design aspects are affected by the choice of robot assembly system. A choice which in turn is affected by various production parameters such as the production volume and the number of parts in the assembly. There are three representative types of robot assembly systems that can be considered in the robot assembly system. The first one is the single station with one robot arm. Second, the single station with two robot arms. Third, collaborative robot. Fourth is the multi-station with robots, special purpose workheads, and manual assembly station as appropriate. For a single station system, parts that require manual handling and assembly and that must be inserted during the assembly cycle present a special problem. For reasons of safety, it would usually be necessary to transfer the assembly to a location or fixture outside the working environment of the robot. Yeah. So this can be accomplished by having the robot place the assembly on a transport device, that carries the assembly to the manual station. After the manual operation has been completed, then the assembly can be returned in a similar manner to within reach of the robot. The use of special purpose workheads for insertion or securing operations presents similar problems to those for manual assembly operation. Two different situations can be accounted. The first involves the insertion or placement of the part by the robot without it being secured immediately. This operation is then followed by a transfer of the assembly to an external workstation to carry out the securing operation. The heavy press fit would be an example. The second situation is where a special purpose workhead is engineered to from the sides of or underneath the work fixture to carry out soldering, tab bending or twisting operation, spin riveting and so on, while the robot has to place and if necessary manipulate the part. So these major problems with a single station system do not occur with a multi-station system, where manual operations or special purpose workheads can be assigned to individual stations as necessary. So this illustrates why it is important to know the type of assembly system likely to be employed when the product is designed. So in this figure, it shows the first figure shows the non-collaborative robot, where you can see there is a safety fences are required to prevent harming human operations, for safety reasons. The second picture, the second picture shows the collaborative robot allowing the human worker to stand in its proximity and work together at the same task. So collaborative robots are now able to work collaboratively with humans, with the assembly worker, without a safety fence. In order to determine the assembly cost, it is necessary to obtain estimates of the following, the total cost of all general purpose equipment. The first one is the total cost of all the general purpose equipment used in the system, including the cost of robots and any transfer devices, and also versatile grippers, all of which can be employed in the assembly of other products if necessary. The second one is the total cost of all the special purpose equipment and tooling, including the special purpose work rates, special fixtures, special robot tools or grippers, special purpose feeders, and special magazines, pallets, or part tray. Then also the cost of the average assembly time, which is the average time to produce a complete product or assembly. Lastly is the cost per assembly of the manual labor involved in machine supervision, loading feeders, magazines, pallets, or part trays, and also performing any manual assembly task. Okay, in addition to the cost of the robot and the special tools or grippers, the cost of the part presentation must be estimated as well. Before this can be accomplished, it must be decided which part presentation method is to be used for each part. In practice, there are usually only two choices. The special purpose feeder or the manually loaded magazine, pallet, or part tray. So the cost associated with part presentation can be divided into two as well. First is the labor cost. The labor cost, which include the material handling, such as loading parts, feeder, or magazines, the system tending, freeing jams in feeders, handling part trays, and etc. And system changeover cost, which is like changing of work fixture, feeders, and magazines, and robot reprogramming. The second cost is the equipment cost, which includes the feeder depreciation and the depreciation of special fixtures, special tooling, magazines, parts, tray, or pallets. Okay, as the summary of design rules for robot assembly, so many of the rules for product design for manual assembly and high-speed automatic assembly also apply to product design for robot assembly. However, when considering the suitability of a proposed design for robot assembly, careful consideration should be given to the needs for any special purpose equipment, such as special grippers or special feeders. So the cost of this equipment must be amortized over the total life volume of the product and for the mid-range volumes where robot assembly might be applied. And this can add considerably to the cost of assembly. So here are the following some specific rules that you can follow during the product design. First, reduce the part count. What it means? This is a major strategy to reduce assembly, manufacture, and overhead costs irrespective of the assembly system to be used. Second, include features such as leads, lips, chamfers, and so on to make parts self-aligning in assembly. Because of the relatively poor repeatability of many robot manipulators, when compared to dedicated workhead mechanism, this is a vitally important measure to ensure consistent fault-free part insertions. The third rule is to ensure that parts which are not secured immediately on insertion are self-locating in the assembly. For multi-station robot assembly system or one-arm single-station system, this is an essential design rule. Holding down of unsecured parts cannot be carried out by a single robot arm, and so special fixturing is required, which must be activated by the robot controller. This adds significantly to special purpose tooling and hence assembly costs. With a two-arm single station, one arm can, on principle, hold down an unsecured part while the other continues the assembly and also the fastening processes. In practice, this requires one arm to change the end of arm tooling to a hold-down device. So the system then proceeds with a 50% efficiency while one arm remains immobile. The fourth rule is the design parts so that you design parts so that they can all be gripped and inserted using the same robot gripper. One major cause of inefficiency in robot assembly system is the need for gripper or tool changes. Even with rapid gripper or tool change system, each change to a special gripper and then back to the standard gripper is approximately equal to 2 assembly operations. Note that the use of screw fasteners always results in the need for tool changes, since robot wrists can seldom rotate more than 1 revolution. The fifth rule is design products so that they can be assembled in layer fashion from directly above the Z-axis assembly. This ensures that the simplest, least costly, and most reliable 4 degrees of freedom robot arms can accomplish the assembly task. It also simplifies the design of the special purpose works fixture. Next, the rules is try to avoid the need for reorienting the partial assembly or for manipulating previously assembled parts. These operations increase the robot assembly cycle time without adding value to the assembly. Moreover, if the partial assembly has to be turned to a different resting aspect during the assembly process, then this will usually result in increased work fixture costs and the need to use more expensive 6 degree of freedom robot arm. 7 rules. Design parts that can be easily handled from bulk. In order to achieve this goal, you should avoid parts that nest or tangle in bulk, parts that are flexible, parts that have thin or tapered edges that can overlap or shingle as they move along a conveyor or feed track, parts that are so delicate or fragile that recirculation in a feeder would cause damage, parts that are sticky or magnetic so that a force comparable to the weight of the part is required for separation, parts which are abrasive and will wear the surfaces of automatic handling system, and parts that are light so that air resistance would create conveying problems, which is about less than 1.5 Newton per meter cube. The eighth rule is if the parts are to be presented using automatic feeders, then you should ensure that they can be oriented using simple tooling. Follow the rules for ease of part orientation discussed earlier. So note that however that feeding and orienting at high speed is seldom necessary in robot assembly, and the main concern is that the features that define part orientation can be easily detected. 9. If parts are to be presented using automatic feeders, then you should ensure that they can be delivered in an orientation from which they can be gripped and inserted without any manipulation. For instance, avoid the situation where a part can only be fed in one orientation from which it must be turned over for insertion. This would require a 6 degree of freedom robot and a special gripper, or a special 180 degrees turn delivery track, which both solutions leading to unnecessary cost increases. Yeah. Lastly, if the parts are to be presented in magazines or part trays, then ensure that they have a stable resting aspect from which they can be gripped and inserted without any manipulation by the robot. If the production conditions are appropriate, the use of robots holds advantages over the use of a special purpose work heads and some design rules can be relaxed. For instance, a robot can be programmed to acquire parts presented in an array, such as in a pallet or part tray which has been loaded manually, thus avoiding many problems arising with automatic feeding from bug. However, when making economic comparisons, the cost of manual loading of the magazines must be taken into account. So that's all for the product design for robot assembly. So thank you.